think about the lithium-ion battery inside your smartphone. It is a delicate, highly precise piece of chemistry that demands a perfectly smooth, steady flow of power to survive. But the electricity waiting for it inside your wall outlet is anything but gentle. It is violent and chaotic. That wall outlet provides alternating current, or AC. In an AC system, the electrical pressure is constantly swinging back and forth, reversing direction dozens of times every second. If you plugged your phone's battery directly into that wild wave, the reversing current would destroy it instantly. Your phone requires direct current, or DC, which flows in only one flat, steady direction. To solve this mismatch, early engineers had to find a way to control the direction of the electricity. Their first real success was the thermionic vacuum tube diode. It was a bulky, fragile glass tube that used heat to boil electrons off a metal plate, forcing them to jump across a vacuum in only one direction. Today, our technology relies on a microscopic, solid-state version of this tool, called the semiconductor diode. The foundational principles for this modern device trace all the way back to 1874, when a German physicist named Ferdinand Braun discovered that certain crystals could conduct electricity asymmetrically. Without a reliable way to translate that wild, reversing AC power into calm, steady DC power, our entire digital ecosystem of phones, laptops, and servers would burn out the moment we turn them on. You can think of a modern semiconductor diode as a strictly enforced one-way check valve for electricity. It has a tiny internal spring, and it only opens when the electrical pressure pushes from the correct side. When electricity pushes in the allowed direction, we call this forward bias. The pressure easily overcomes the valve, and the current flows through with almost no resistance. But the moment the electricity tries to flow backward, we enter reverse bias. The backward pressure forces the internal valve to slam completely shut, blocking the flow entirely. This graph shows the VI, or voltage current characteristic curve, which is the exact mathematical blueprint engineers use to map this behavior. On the left side, representing reverse bias, the current sits flat at 0. But on the right side, representing forward bias, you see an exponentially rising curve where the electricity flows freely. An ideal, perfectly magical valve would open the second any forward pressure was applied. But on this chart, you'll notice the practical reality. The curve doesn't actually start rising until it hits exactly 0.7 volts. That is called the barrier potential. It is a tiny electrical toll you have to pay just to compress that internal spring and force the diode open. By relying on this extremely predictable one-way behavior, engineers can use diodes as physical tools to sculpt raw electrical waves into exactly the shapes we need. So, how do we actually turn that violently fluctuating AC sine wave from the wall into the flat DC power your phone needs? We have to build a rectifier circuit. The simplest approach is a halfway rectifier. If we place a single diode in the path of the AC wave, it allows the forward-pushing positive half to pass through. But when the wave tries to reverse direction, the diode snaps shut and completely slices off that negative half. The problem with this method is that it throws away a massive amount of energy. Because we are entirely blocking the reverse flow, exactly half of the available electrical power from the wall outlet is wasted. To fix this inefficiency, electrical engineers designed the full-wave bridge rectifier. Instead of one diode, this clever solution uses an arrangement of exactly 4 diodes working together. This diamond-shaped bridge acts like a one-way traffic circle. When the positive half of the wave comes in, 2 diodes guide it to the exit. When the negative backward half arrives, the other 2 diodes catch it and physically fold it over. It forces them upward so that all the power from both halves of the wave now flows forward in a continuous series of positive hills. We successfully stopped the electricity from flowing backward. But this bouncing, pulsating wave is still way too erratic to safely plug into your phone's battery. We have more sculpting to do. To make this power usable, our next step is to smooth out those aggressive pulsating hills created by the bridge rectifier. We do this by adding a smoothing capacitor to the circuit. Think of a capacitor as an electrical sponge. When the voltage peaks, the sponge soaks up the excess pressure. Then, as the wave starts to dip into a valley, the sponge slowly drains out its stored energy, filling in the gaps and turning those steep drops into a gentle rolling ripple. That gentle ripple is a huge improvement, but modern microprocessors are incredibly sensitive. Even a slight waver in voltage can cause digital errors or fraud in microscopic components. To get a perfectly flat line, we bring in our final sculpting tool, the voltage regulator. This relies on a highly specialized component called a Zener diode. Remember how normal diodes block reverse voltage? A Zener diode is intentionally designed to break that rule safely. It acts as a precision pressure relief valve. When placed backward in the circuit, it simply opens up and shaves off the remaining ripple, locking the voltage at an exact, unwavering value. That specific sequence, chopping the wave, folding it over, smoothing the drops, and shaving it flat, is the exact hidden physical process happening inside every single phone charging brick in the world. Diodes do an incredible job converting bulk power from the wall, but their utility extends far beyond your charger. They are also heavily relied upon for the delicate task of managing internal data signals inside radios, televisions, and computers. Managing these low-voltage data streams requires vast, intricate networks of diodes. In the early days of digital computing, stringing thousands of these physical valves together was the only way to perform logic operations, which is why early mainframe computers required entire rooms to house them. One of the most common ways diodes protect these fragile data signals is in a circuit called a diode limiter, which is sometimes called a clipper. A clipper acts exactly like a pair of electrical scissors. If static electricity or interference creates a rogue, oversized voltage spike that threatens a sensitive chip, the diode clipper instantaneously snips off the top of the wave the moment it exceeds a safe, predetermined limit. Alternatively, sometimes the physical shape of your signal is perfectly fine, but its baseline voltage level is entirely wrong for the next component in the sequence. For that, we use a diode clamper. Instead of scissors, a clamper acts like an elevator. By pairing a diode with a capacitor, the circuit physically shifts the entire waveform up or down the voltage scale, securing it to a brand new baseline without altering its original shape at all. Whether they are clipping dangerous spikes or elevating data streams, diodes are precise surgical instruments used to shape, move, and protect information. At its core, the diode is simply a strict one-way valve. It is a basic tool that grants us absolute physical control over the direction and the shape of electricity. By slamming chaotic alternating current into a rigid unidirectional barrier, we force the raw forces of nature to obey mathematical rules. Every microprocessor, every server farm, and every screen you look at demands absolute stability to function. Without the diode's silent, continuous ability to sculpt and refine that raw electrical power, the precision-driven digital world we rely on simply could not exist.